Alright, let's continue. Where is it? I think this one. Okay, we are in concurrency. The last time. Oh, wait a minute. This one, right. Okay. Volatile. I kind of forgot what this does. Let me check. Can be read or modified asynchronously by something other than the current thread of execution. Oh. Okay, interesting. Involving situation where the value can change without action from the visible code. Well, there is another thread running that also uses the variable as a signal handler that may change the value of the variable. And that is the address. Oh. Volatile. What you wrote? What you wrote? Okay. In which data and comment are written. Alright, now to issue comment with the previous data value. Also take a look at the width while passing be optimized out. Okay then. Tell the compiler that this variable as is. Maybe something like that. I haven't tried volatile keyword yet, so I'm not really sure. Okay, in loops. Common thread. Wait a minute. Let me open this. Okay. Alright. We are currently in this one. Okay. Wait, let me also open this. Where is the code? think this one. Okay. This is the first. What is it called? The first snippet. Why the indentation like this? Okay. Common.h. Alright. The spin function is from the common.h. Okay. This one. Using double. Okay, right. I mean, in the previous one, I think this one, right? We don't really need to use this. See the CPU.c. We don't need this because, well, looks like we already using that in here. Common.h, the header, right? And from the code, yeah, there is no system header either. So no answer. Okay. And then this one is the memory one. Yeah, looks like we don't really need this too. And then this one. The memory one, mem.c. It can be used. Wait, what is it called? Which can use the same memory address even though it is on different process. Thing like that. The space randomization is disabled. Okay, now let's take a look at concurrency. Common threads header. Okay. Using a macro. Oh. Okay. Semaphore. It's right. Oh, okay. what things in it. It's the volatile, marker, okay, white pointer, this one too, plus, counter, plus, okay, I don't know. Main. That value, okay. Thread underscore T, okay. Initial value. Thread underscore create. This one. And then assert equals 0. Okay. We are creating a new thread for concurrency. Okay. Let me check. Create a new thread, right? Nice to meet. Calling again. The thread underscore create. Function start a new thread in the calling process. Invoking start. Okay, and then join with a terminated thread. With a terminated thread. Interesting. Function waits for the thread specified by thread to terminate. Thread to terminate, Okay. Final value counter. Another main theme of this book is concurrency. Okay. We use this conceptual term to refer to a host of problems that arise and must be addressed when working on many things at once, concurrently, okay? In the same program. The problem of concurrency arose first within the operating system itself. As you can see in the example above on virtualization, the operating system is juggling many things at once, first running one process, then another, and so forth. As it turns out, doing so led to some deep and interesting problem. Okay. Unfortunately, the problem of concurrency are no longer limited just to the operating system itself. Indeed, modern multi-thread program exhibit the same problems. Let us demonstrate with an example of a multi-thread program. This one, right? Indeed, modern multi-thread program exhibit the same problem. Okay. Although you might not understand this example fully at the moment, and we'll learn a lot more about it in later chapters. I think it is in, where is it? This one, right? The second piece from the 3 pieces of the book. Okay. In the section of the book on concurrency, the basic idea is simple. The main program creates 2 threads using pthread create, right? It's basically pthread create instead of the assert function. So if this is false, we will throw an error, something like that. Let me check. Is it false or true? If expression is false, okay. Expression is false. So this will false if the return value is not equal to 0, as far as I understand. Okay. Anyway, you can think of a thread as a function running within the same memory space. You can think of a thread as a function running within the same memory space as other function. As other function. Thread as a function running in the same memory space as other function, with more than one of them active at a time. In this example, each thread starts running in a routine called worker. Okay, let me check again this one, right? Oh. Wait. Okay. This one is the Okay, attribute, maybe start routine. Oh, okay. In which it simply increment a counter in a loop for loops number of time. There are loops, and now, depending on the argument for the program. Okay, like this one. Each thread start running in a routine called worker, in which it simply increments a counter in a loop for loops number of times. Below is a transcript of what happens when we run this program with the input value for the variable loops set to 1000. Oh, the value of loops determine how many times each of the two worker will increment the set counter in a loop. When the program is run with the value of loop set to 1000, what do you expect the final value of counter to be? 2000. Oh, we increment the counter input. What is it called? P1 and P2. Is that it? That's why there is this volatile. Maybe. As you probably guess, when the two threads are finished, the final value of the counter is 2000. As each thread increments the counter 1000 times. Indeed, when the input value of loops is set to n, we would expect the final output of the program to be to n. But life is not so simple. Okay, as it turns out. Let's run the same program but with higher values for loops and see what happens. Okay, threads. What is it called? 100,000. Final value. Oh. Wait a minute. Okay, interesting. In this run, when we give an input value of 100,000, instead of getting a final value of 200,000, we instead first get this one, 143 and 12,000. Then when we run the program a second time, we not only again get the wrong value, but a different value than the last time. In fact, if you run the program over and over with high values of loops, you may find that sometimes you even get the right answer. Sometimes get the right answer. So there's a chance we still get the right answer. Interesting. So why is this happening? As it turns out, the reason for these odd and unusual outcomes relate to how instructions are executed, with each one at a time. These odd and unusual outcomes relate to how instructions are executed, with each one at a time. Unfortunately, a key part of the program above, where the set counter is increment, that should be the lower. Let me finish this. Where the set counter is increment, takes 3 instructions. One to load the value of the counter from memory into register, one to increment it, and one to store it back into memory. Because these 3 instructions do not execute automatically at once. Okay. So it is not an atomic operation. It is running everything at the same time. Something like that. Strange thing can happen. It is this problem of concurrency that we will address in greater detail in the second part of this book. Okay. The actual call should be to lowercase bitrate grid. The uppercase version is our own wrapper that calls bitrate underscore grid and make sure that the written code indicates the call succeed. See the code for the tail in this one, right? Just a wrapper with assert function. Okay. The crux of the problem: how to build correct concurrent program. When there are many concurrently executing threads within the same memory space, how can we build a correctly working program? Okay, concurrently executing threads within the same memory space. How can we build a correctly working program? What primitives are needed from the operating system? What mechanisms should be provided by the hardware? By the hardware. Okay. I'm still not sure what the primitive in here means. What primitive are needed from the operating system? How can we use them to solve the problem of concurrency? Okay. Now let's take a look at persistence. This one. The Thought matter thing. Oh. Hello Luigi, welcome. How are you, bro? Well, I'm still coughing sometimes. But yeah, other than that is I'm fine, I guess. Where do you find out these interesting documentary resources? I'm just browsing, I guess. I read some, what is it called? I read some answer from Stack Overflow and someone points to some resource or document and I looking from there, I guess. So it is mostly from a forum where I find all this interesting document or resource and then looking at the reference from the forum and gaining more document or resource from there. So yeah, usually it is start from the forum like Stack Overflow or something like that. I know a course called Mental Tetris. It's so cool. Basically, to make you build a whole computer from zero. With its operating system starting from none. So I have about IDE. Oh, I've heard about that. Mental Tetris. Let's take a look. This one, right? Wait, let me copy this in the chat. If anyone wants to take a look. Yeah, I know about this, but I haven't take a look at this. Oh, they also have an IDE. Okay. Yeah, I know about this, but personally I haven't taken a look at this book, at this resource, I guess. I mean, one resource at a time, right? This is the IDE, I think. Okay, interesting. Wait, let me. Oh. Okay, this is the IDE. Okay, interesting. Wait a minute. Oh. Okay. These are the software package. Okay, where? Sponge2F project. Into book chapter. Wait, is this the book? I mean, or maybe we can just take a look from the project here. Have you tried this, Luigi? Or you just found this out? Oh, yes, you started. Okay. Did you start another abstraction? Okay. Did you start from the project here or with the book? This book? I mean, I think that's what confused me. Oh, a Coursera course. Oh, okay. Watching the course on Coursera. Alright. maybe I will take a look at this, but for now I want to focus on the other book, this book, right? Operating System 3 Easy Pieces. Yeah, I mean, there are a lot of interesting resources, so we need to take one resource at a time. Otherwise, we will overwhelm. Like, what should we do first, right? One thing at a time, yeah. Okay, let's continue this one. Persistence. The third major theme of the course is persistence. In system memory, data can be easily lost, as devices as DRAM store values in a volatile manner. Okay. When power goes away or the system crashes, any data in memory is lost. Okay. Thus, we need hardware and software to be able to store data persistently. Maybe something like saving a file, something like that. Such storage is thus critical to any system as users care a great deal about their data. Oh, okay. Thus critical to their data. The hardware comes in the form of some kind of input or output, the I/O, right? The I/O device. In modern system, a hard drive is a common repository for long-lived information. And the solid-state drive, the SSD, which currently most likely become expensive. Yeah, after the RAM price hike, now the SSD starting to get expensive. Oh my god. Okay, and the SSD are making headway in this arena as well. The software in the operating system. Now we go back to the hard drive. Then flip-flop, yeah. When the SSD become expensive, we go to the hard drive, and then we go to the flip-flop when the hard drive become expensive too. Okay. Yeah. What an interesting world or era we are live in. The software in the operating system that usually manages the disk is called the file system. Yeah. It is thus responsible for storing any files the user creates in a reliable and efficient manner on the disk of the system. Okay, unlike the abstraction provided by the operating system for the CPU and memory, the operating system does not create a private virtualized disk for its application. Oh, unlike the abstraction provided by the operating system for the CPU and memory, the operating system does not create a private virtualized disk for its application. Okay, so there is no virtual disk or something like that. Okay. Rather, it is assumed that oftentimes user will want to share information that is in files. For example, when writing a C program, you might first use an editor. Well, in this book, we are using Emacs, or the author using Emacs, right? The GNU Emacs, okay. This is the command to run the C, to open main.c file. Once done, you make use the compiler to turn the source code into an executable. Right, using GCC. This one. This is the output. The output name of the executable, or maybe we can just say this is the executable name. That's easier to understand, I guess. This is the executable name. We provide this with the flag -o, and then this is the source code name. When we are finished, you might run the new executable like this one, /main for this one. Right, we got the main from this expression, something like that. Thus, you can see how files are shared across different processes. First, Emacs create a file that serves as input to the compiler. The compiler uses that input file to create a new executable file. In many steps, take a compiler course for the tiles. Finally, the new executable is then run. First, Emacs create a file, okay, that serves as input to the compiler, right, this one. And then the compiler uses that input file to create a new executable file. In many steps, take a compiler course for the tiles, okay. Finally, the new executable is then run, and thus a new program is born. Okay. So, okay, wait a minute. Files are shared across different processes, right? We might still opening this main.c file in Emacs, right? And we also use the, use main.c file when we compile those files, So we share across different processes in the Emacs process and the GCC process, as far as I understand. Okay, you should be using Emacs. If you're using VI, there is probably something wrong with you. Okay, if you're using something that is not a real good editor, that is even worse. Oh my god. Yeah. We should be using Emacs, everyone. If we are using VI or Vim, there is something wrong with us. Yeah, well, maybe there is something wrong with me, but I am fine with something wrong with myself. Okay. good. Okay, this one. Oh, fcntr.h. Interesting. What is that? CNTR. Oh, file control. Okay. Shall perform the operation described below on open file. Is a file descriptor. Oh, okay. File control. Oh. Wait. There's also Perl. Oh, interesting. Let's take a look at the system call. Something like this. Manipulate file descriptor. Okay. Okay. A support. Duplicating file descriptor. Okay. Status flag. Right, okay. We use open. Is open in this header? Let me check. Oh, it is in the CNTR header. Okay. We open a temporary file. Okay. Or maybe to be precise, a file in the /temp directory. And then, oh, this is the flag we provide. Right. And then this one is mode. I am still not sure what this mode does. But anyway, if the FT more than -1. Oh. Wait, what is the return value again? And a small non-negative integer. Okay, so if it is equal to -1 or less than -1, any negative value maybe it will fail, right? Right. Okay. We are putting this, what is it called? This text into the file that we open, right? I think this is the number of character 1, 2, 3, and then this. Okay, 5, 6. Okay, here's 12. If not equal 12, throw an error again, and then we close the file and return 0. A program that does input-output, the io1.c. To understand this better, let's look at some code. Figure 2.6, this one, presents code to create a file in the temp directory, right, that contains string hello world. accomplish this task, the program makes 3 calls into the operating system. 3 calls into the operating system, which is open, to open the file or creates it if the file did not exist. I assume maybe that is what this mode does. Oh, no, maybe this one. Maybe. Is this something like concat? Yeah, I'm still not sure how the open function works. Open file and creates it if it not exists yet. I assume the second is right. This one, the write function, write some data to the file that is closed. Simply close the file, thus indicating the program won't be writing any more data to it. These system calls are route to the part of the operating system called the file system. Okay, which then, by the way, is there some situation in C or C++ where you interact directly with the kernel without using any abstraction? I am not sure. I mean, if I remember correctly, we can embed assembly directly into the C or maybe C++2 source code, inline assembly. And I think I've done that previously. Give the ability to embed assembly language source code within a C program. So maybe we can do that using assembly if you don't want to use any abstraction. I think what is it called? I've done that, or at least try doing that like this. Assembly, like doing printf without the library or something like that. As far as I understand, yeah, we can use assembly to talk directly with the kernel. I mean, I'm still not sure either. Well, let's find out. C programming, interact directly with kernel. I mean with this. Maybe I should open in here. Where is it? The playground. printf. Yeah, let me copy this in the chat. So I've tried an example from some YouTube video, right? We can kind of replace printf with this assembly. with this assembly. So we are not using any library at all with this C source code. So maybe we can talk directly with the kernel using assembly without any library or API. But yeah, that can be dangerous, I guess. Talk with non-S system. Mostly to understand it more, not to type. Okay. Interact with the kernel. Open, read, write, okay. So the shell is language code enough to interact with the kernel. If you want to call the system call directly, not the libc wrappers, your choice are generally C. C++, not even linking with the standard library or assembler, right? But going this way makes little sense even as exercise, unless you want to write your own libc or something. Okay, so yeah, as far as I understand, we can use assembly to interact directly without the library, the libc, C library wrapper. But then again, it can be dangerous because the C library usually have some sort of safety guard, you know. First, decide what your goal. Interacting with kernel myself. Okay, and there's also this one, Linux device driver. And copy this in the chat. At the end of the day, all what these libraries do is moving things in memory, allocating and deallocating, and moving files. Right? Maybe. I mean, I'm not sure either. Maybe there is other things that this library do other than, well, interacting with the memory or file maybe. And yeah, I'm not sure. I mean, we are learning together, right? Okay. But yeah, that can be an interesting hypothesis for now. I mean, we need to prove that, right? Okay, introduction to device driver and so on. So, if you want to learn about Linux device driver, you can take a look at this book. Okay. Oh, alright. Thank you, Richie. Okay. The system called unrooted to the part of the operating system called file system. which then handles the request and return some kind of error code to the user. A route to the part of the operating system called the file system, which then handles the request and return some kind of error code to the user. Okay. You might be wondering what the operating system does in order to actually write to TIX. We would show you, but you'd have to promise to close your eyes first. It is that unpleasant. It is that unpleasant. Okay. Embrace ourselves, everyone. The file system has to do a fair bit of work. First, figuring out where on TIX this new data will reside, and then keeping track of it in various structures the file system maintains. Doing so requires issuing input-output requests to the underlying storage device to either read existing structure or update or write them. Wait a minute. The file system has to do a fair bit of work. First of all, where on TIX this new data will reside. Okay. Maybe something like the address. Maybe. Okay. Where on TIX this new data will reside. And then keeping track of it in various structure the file system maintains. Okay. Again, for example, in this one, right, main.c file is accessed by Emacs and also GCC. So the operating system keeping track of the main.c state, I guess. Where is it? See, this one, keeping track of it in various structures the file system maintains. Doing so requires issuing input-output requests to the underlying storage device to either read existing structure or update them. As anyone who has written a device driver knows, getting a device to do something on your behalf is an intricate and detailed process. Right? I don't have any experience, but I assume, or maybe I imagine it needs to be some kind of detail process, right? Which can be challenging. Okay, it requires a deep knowledge of the low-level device interface and its exact semantics. Fortunately, the operating system provides a standard and simple way to access the device through its system call. Thus, the operating system is sometimes seen as a standard library. Okay. Yeah, usually the library makes things easier to interact with the operating system, but again, if we want to learn how to create those library, or maybe the driver, right? We can take a look at this book. I mean, I haven't taken a look at this book yet, so I'm not sure. But keep in mind that this book is based on the old Linux kernel version, so we need to adapt to the new Linux kernel version. Okay. Of course, there are many more details in how devices are accessed and how file system manages data persistently atop said device. For performance reasons, most file systems first delay such writes for a while, hoping to patch them into larger groups. Okay, wait a minute. There are many more details in how devices are accessed and how file system manage data persistently atop said device. The access, right? And then manage the data persistently. Okay. For performance reasons, most file systems first delay such writes for a while, hoping to patch them into larger groups. To handle the problems of system crashes during writes. Okay, wait a minute. For performance reasons, most file systems first delay. Okay. Delay such writes for a while, hoping to patch them into larger groups. Okay. So what is it called? We collect, I guess, until a certain amount of data, and then we write them per batch with those amount of data. To a certain amount of data, I think. Okay, to handle the problem of system crashes during writes, right? Most file systems incorporate some kind of intricate write protocol, such as journaling or copy on write. Carefully ordering writes to text to ensure that if a failure occurs during the write sequence, the system can recover to reasonable state afterward. Okay, right? Copy on write. So instead of writing directly to the file, the file system or maybe the write protocol copy the file first and then writing to those copy instead of the original, and then if the writing done, those copy replace the original one. Maybe something like that. Copy on write in this, what is it called? In this mechanism means. So if the write fail, we don't, what is it called? We still have those original file before we are doing any write or adding the content into the file. To make different common operations efficient, file system employ many different data structure and access method, from simple list to complex B-trees. Okay. I am still not sure what B-trees is. Right, okay. File system. Is the Linux file system just a further hierarchy that it has? Oh, you mean, what is it called? I kind of forgot. Wait a minute. If I... Okay, maybe something like this. Wait a minute. Man. Something like this. Oh, there is no entry, okay. File system hierarchy. If I can type correctly, I think this one. I forgot there's the main page for this. Now let me copy this in the chat. Linux file system, just a folder hierarchy that it has. I'm not sure yet. I heard that in Linux everything is a file. Yeah, as far as I understand, that is the case. But there is, what is it called? There's different kind of file. I forgot. Where is it? I think ls. No, comment. Yeah. There are different kind of files. And I forgot what is the file is. Maybe in this one. Oh no. Don't think this one. There is this list for the file. Like there is this dictionary file, right? Dictionaries, not dictionary, directory. Directory can be considered as a file or a special file, you could say, not a regular file. Oh, maybe this one. The file type is one of the following character. See, there is regular file. For example, let's take a look at this. Right. What is it? Let's just use readme. Okay. If there is this right at the beginning, this means this is a regular file. the readme.md is regular file, right? And then if the the beginning of this is not test but let's say B or D, right, or directory. Okay. I don't know how to navigate this. This didn't use. Yeah, let me try again. Okay. We didn't use the the Vmotion here, so I'm kind of struggling. Yeah, where is it? Okay, this one. If the beginning is D, for example, maybe something like this. Not that one. Something like this, right? This is D. Then it is a directory file. So directory can be considered as a file, a special file, something like that maybe. So yeah, even though everything is a file, it have different type of file, like block special file, character special file, and directory file, or this FIFO file, something like that. Hello, welcome, Josie. Oh, you're reading this book too? Well, let's read together, I guess. Yeah, currently we are in, in the section 2.4, the persistent section. So yeah, we haven't gone that far yet. Okay, P3s. Wait a minute. And how your file system actually stores stuff? Okay, so the book I mentioned about P3s, and I'm kind of curious what P3s is. Let me copy this in the chat. Okay, P3s and how your file system actually stores stuff. Wait, the URL in the chat is there, right? I mean, I hope the URL is copied into the chat. You click on a file and it opens. You save a document and it's there the next time you look. Oh, okay. Yeah, I mean, if someone else copy URL into the chat will disappear. So I'm kind of afraid that YouTube also treat my chat the same thing. Fortunately, YouTube did not do that, so I can still share the URL in the chat. Yeah. when someone else trying to share a URL, the message got deleted. And I guess the exception is what is it called? Is the one in the channel, the one running the channel, something like that. And well, that's, yeah. Hopefully YouTube didn't change that behavior. I mean, if I can send URL in the chat too, that will be problematic. Okay, you save a document and it's there the next time you look. This seemingly magical process happening countless times a day is orchestrated by your operating system file system, a complex piece of software designed to organize and manage data on persistent storage. But how does it actually work? How does it efficiently locate a specific piece of data among potentially terabytes of information without scanning everything? The unsung hero behind this efficiency is often a data structure called the B-tree. Let's peel back the layers and understand why B-trees are indispensable for how your computer stores stuff. Telephone in the room. Text input-output is slow. Okay. First we dive into B-trees. We need to understand the fundamental problem they solve. Okay. Computers operate at vastly different speed. Alright. Your CPU executes billions of instructions per second. Okay. And RAM, or random access memory, can be accessed in nanoseconds. Oh. So not seconds, but nanoseconds. Okay. However, persistent storage, like hard disk drive or SSD, or even solid-state drive SSD, operates on much lower scale, typically in microseconds for SSD and milliseconds for SSD. Okay. The biggest performance bottleneck, especially with traditional SSD, is seeking. Oh, okay. A mechanical SSD has spinning platters and read or write heads that must physically move to the correct track and sector to read or write data. This physical movement takes a significant amount of time compared to electronic operation. Okay. Even SSD, while much faster, still have higher latency and different access pattern compared to RAM. Okay, this make me curious. If we can make RAM faster, what is the constraint of making SSD as fast as RAM? Is it because RAM is not really store persistent data, so we can make it fast? But for SSD, we need to make sure that the data stay for a long period of time. maybe I think the benefit is that the text content will get loaded faster in RAM. Oh, okay. Well, what is it called? Yeah, the benefit, the text content will get loaded faster in RAM. So we are putting the content in the RAM. So like if you have something that is smaller on text in RAM, it will be loaded faster. So let's see overall. Okay. Well, I'm more curious in terms of maybe the hardware perspective. I mean, again, we put, well, as far as I understand, put RAM and SSD using the electronic operation, right? The RAM can be fast, but the SSD, what is it called? Slower than the RAM or not as fast as the RAM. So what kind of technical difficulties that making SSD as fast as RAM in terms of the hardware? And it's just my curiosity, I guess. I mean, both of it using electronic operation, right? So that's what I'm curious about. I think it's impossible because the CPU to access the SSD has to pass through the I/O bus. Oh, okay. Maybe that's the case. The input-output bus. Wait, but isn't the RAM is the same? Need to pass the input-output or not? Yeah, I'm still not sure if we need to pass the input-output to access the RAM or not. Okay, that is one of the hypotheses. Okay, therefore, any data structure designed for persistent storage must prioritize minimizing disk input-output operation, read and write. It is far better to read one large chunk of data from disk than many small scattered chunks. Oh, even if the total amount of data is the same. Okay, interesting. So it is better to read one large chunk rather than many small scattered chunks. Alright. This is related to disk input-output operation. Okay. This is where the concept of a disk block or page comes into play. File system typically read and write data in fixed size blocks. Oh, okay. Kilobyte, 8 kilobyte, 16 kilobyte. Fixed size block. Alright. So maybe this is what it means. Where is it called? The beds. Okay, this one. We are, what is it? Slicing that per beds, right? With the fixed size blocks. Okay. By the way, a byte is exactly 8 bits. I still have no idea, but some people say that on another system, a byte might not be 8 bits. Okay, we can check that. Why 1 byte equal to 8 bits on most system? And I think, okay. What is the story way? Okay, maybe this one. And I think there is, what is it called? I think some people said if we want to check 1 byte, we can check at the char bit in the limits.h header. Because 1 char in C is 1 byte, and the char bit have the value of 1 byte. It is in this case, again, bits, right? Number of bits. In this case, 8 bits. So if the system char bit is not 8 bits, then yeah, 1 byte is not 8 bits. One thing to keep in mind, I guess. But again, I don't have any experience yet, so I'm not sure what kind of system that doesn't have 8 bits, doesn't have 1 byte as 8 bits. Okay, what were the historical force at work? The threat of to make in deciding to use group of 8 bits as the fundamental unit. Let me copy this in the chat. There were machines once upon a time using other word size, but today for non-8-byteness. You must look to museum pieces, specialized chip for embedded application, right? Usually in the embedded system, the 1 byte might not be 8 bit. And DSP, oh, digital signal processor, okay. DSP also the microprocessor, oh, okay, yeah. Anything specialized or embedded, maybe. The non-8-bitness. Okay. How did the byte evolve out of chaos and creativity of the early days of computer design? I can imagine that fewer bits would be ineffective for handling enough data to make computing feasible, while too many would have led to expensive hardware. Were other interests in play? Why did this force balance out to 8 bits? But if I could time travel, I would go back to when the byte was declared to be 8 bits and convinced everyone to make it 12 bits, prepping to meet some early 21st century thinkers. I mean, why would you choose 12 bits instead of 8 bits? That is another question. Maybe one of the questions where we can answer it better than good old Wikipedia. So why would you prefer 12-bit to 8-bit, right? Well, why would this person prefer 12-bit to 8 bits? Yeah, I was going to say it was the IBM 360, of which Stretch was the forerunner, but Wikipedia got it all in there. PTP-11, which broke bytes into the non-punch card word, Unified, which has 9-bit bytes, right? Unified is the last sentence in chess. Would be inconvenient because it's not power of 2. Memory registers weren't so cheap back then, so I mean, nowadays memory is also not cheap, so we are going back in history. Maybe. 8-bit was a good compromise compared to 6 or 9. Fraction of 36-bit. Does it matter if it is a power of 2? I assume because of binary. Maybe. Yeah, why everything need to be power of 2? Yeah, I'm still not sure. My hypothesis is because of the binary operation is the shortest operation out there, so it can be fast running the binary operation rather than the usual decimal operation. Maybe something like that. I mean, it is a hypothesis which might be wrong. I mean, I'm too young for understanding the history. Okay, or maybe not understanding, verify the story. What is right and what is wrong from the history. I wonder how we as humans were able to make all these complex things. I mean, that is the power of human intelligence, I guess. We are basically creating something that doesn't exist in the world, right? Or maybe human imagination. Yeah, I'm not sure. But there is something in the human mind that can create something new, that doesn't exist yet. And that counts when you're making logic out of raw transistor in little cans. Back when I first learned digital electronics, logic gates usually came 4 to 3 or 3 to chip, or 6 inverters on a chip. Handling 12-bit would have been double different way. As for addressing and power of two word size, those early pioneers used address to individual bits. Using word size that were power of 2 were not so important in the early days. Power of 2 were not so important in the early days. The TEC-10 had a 36-bit word. Not 32-bit, but 36. Okay. And 60-bit words. An index register with 18 bits. I really wonder why 10 bits for a byte were never considered. Number of bits should not be power of 2. Don't need to address bits, only bytes. 10-bit bytes would be very good for beginner in computers. 1 byte can address 1 kilobyte. 2 bytes can address 1 megabyte etc. It just feels so natural and ease understanding and programming. I'm not sure if 10-bit would make it easier to understand. Maybe, we are using a decimal operation, right? The 10, what is it called? 10 base operation for basic arithmetic. Maybe it can be easier if we use 10 bits for a byte. We can use digits and letters for representation as we do with hex base 32 encoding. 10 bits byte looks like a fair and convenient compromise. We will have the chip soon. Building a mental model of mutation, especially when most mainstream languages abuse the equal sign for something that's very much not equality. Okay, pointers or reference or aliasing and recursion are much bigger hurdles to beginning programmers. Beginners don't even need to understand there's a limit to 32-bit integer just yet. Right. If the beginner need to think about the limit of integer, then they might be overwhelmed, one step at a time. And in any exercise where it would matter, they don't need to know the precise number since they should be comparing against a predefined constant. In bit set, okay. 132-bit words. A lot of really early work was done with 5-bit code codes, but those quickly become quite limiting. Only 32 possible characters. So basically only uppercase letters and a few punctuation marks, but not enough space for digits. From there, quite a few machines went to 6-bit characters. This was still pretty inadequate though. If you want upper and lower case, English letter and digit, that left only 2 more characters for punctuation. So most still had only 1 case of letter in character set. As to find a 7-bit character set. that was good enough for a lot of use for a long time and has formed the basis of most newer character sets as well. Binary computers motivate the sender to making size power of 2. Okay. Because of the binary operation, I assume. Okay. That's why we are using the size of the power of 2 for the size. Since the standard character set requires 7-bit anyway, it wasn't much of a stress to add one more bit to get power of 2. And by then storage was becoming enough cheaper that wasting a bit for most characters was well acceptable as well. Since then, character sets have moved to 16 and 32 bits, but most mainstream computers are largely based on the original IBM PC. Then again, enough of the market is sufficiently satisfied with 8-bit character that even the PC hasn't come to its current level of dominance. I'm not sure everybody will do everything with larger characters anyway. Okay. I should also add that the market has changed quite a bit, better hardware than the software. Moved to 16-bit character long ago. The interest in supporting minimally from the difficulties inherent. Okay. Then you add in fact that for some language or character set, even the basic idea of upper or lower case don't apply. Okay, so maybe it's because of the ASCII standard that we have the 8-bit for 1 byte on most system or most machine, I guess. But yeah, for the accuracy of that, I'm not really sure. Plus a validation bit. Oh, the early transmission protocol were not as lossless as the designers want. It is called a parity bit. Okay. For crude forms of error detection recovery. Okay, so most likely for the Ricci equation, why a byte is exactly 8 bits on most system? Most likely because of the ASCII standard. I mean, there are other machines that doesn't have 8-bit for 1 byte, but most systems that following the ASCII standard have 8-bit as 1 byte. Again, this is just a hypothesis. Seven bit for ASCII information and 1 for error detecting parity. We are learning history too. So here, in some machine, it is, what is it called? We might not have 8-bit as 1 byte, in embedded system or embedded machine or DSP, right? So we can take a look at the char bit to make sure that how many bits we have for 1 byte, because char in C is 1 byte, if I remember correctly. Okay, let's continue this. Enter bit trees. Don't forget to drink water. Okay. Enter bit trees. The sign for ticks. Bit is short for balance tree. Okay. The B is still the bit, but balance is the most widely accepted meaning. Okay. So it is still the bit. It's a self-balancing tree data structure that maintains sorted data and allows search, sequential access, insertion, and deletion in logarithmic time. What makes them uniquely suited for disk-based storage is their multi-way nature. Multi-way nature. Unlike binary search trees, which have at most 2 children per node, bit trees can have many children, often 100 or 1,000. This fan-out property is crucial. Each node in a bit tree is designed to correspond to a single disk block or page. Each node in a bit tree is designed to correspond to a single disk or page. Okay. By having a high order, I assume this is the smallest size in the storage. Maybe, we haven't taken a look at the page yet, right? What is page in the book? I think at some point we will take a look at what is page. This one, paging. Simple example and overview. Maybe. So we haven't taken a look at that yet. By having a high order, meaning a large number of keys and children per node, a bit tree can achieve a very shallow heap for a vast amount of data. Why is a shallow heap good for this? Because it's not traversal. Often means a disk input-output operation. If a tree has a height of 8, then searching for a piece of data will require 8 disk reads in the worst case. A shallow tree minimizes this expensive disk sake. Oh, okay. Is that why read one large chunk is better than many small scattered chunks? Okay. B-tree's properties simplified for understanding. Okay. Hague found out its internal node can have a large number of children, denoted by M or T. This M is chosen so that a node roughly fills a disk block. Balanced leaf nodes are at the same depth. This ensures that the worst case search time is predictable and minimized. Keys within each node are stored in sorted order. Insertion and deletion automatically adjust the tree structure, splitting or merging nodes to maintain balance and properties. Consider a B-tree where each node can hold 100 keys. Hague 1 root only can store 100 keys. Hague 2, the root can point to 101 children nodes. Each of these 101 nodes can store 100 keys. Okay. Hague 3 each of those 101 nodes can point to another 101 children. That is this one. Okay. Quickly the capacity grows with minimal increase in height. For a tree with millions or billions of items, the height might still only be 3 or 4, meaning only 3 or 4 disk reads to find any item. Okay, design for efficiency. To find a key, you start at the root and lead the root into a memory and perform a binary search within the node's key to determine which child pointer to follow. You repeat this until you reach a leaf node. Okay, because each node reads a disk input-output and the tree height is minimal. Searches are very fast. Insertion. When a new key is inserted, it's typically added to a leaf node. If that leaf node becomes full, exceeds its maximum capacity, it splits into 2 nodes, and the median key is pushed up to the parent nodes. The splitting can propagate up to the root, potentially increasing the tree's height by 1 if the root splits. Added to a leaf node. If that leaf node becomes full, exceed maximum capacity, in this case we assume 100k, 100 capacity for the node. It's spaced into 2 nodes. Okay. And the median key is pushed up to the parent node. The splitting can propagate up to the root, potentially increasing the tree's height by 1 if the root splits. Okay. Increasing the tree's height by 1 if the root splits. Okay. The lesson involves removing a key if a node becomes underfull, falls below minimum capacity. In this example, 100, right? Below 100, it attempts to borrow a key from a sibling and or merge with a sibling. To borrow a key from a sibling or merge with a sibling. Okay. This process can propagate down or up the tree to maintain the minimum fill factor. Alright. The brilliance of B3 lies in this dynamic operation which ensures the tree remains balanced and optimal for disk access even as data is added and removed. B3 in file system, where the magic happens. File system use B3s or closely related variants like B plus trees for various critical tasks. Directory structure. When you navigate through directories, the file system needs to quickly list the contents and file specific files. Directory entries, file names mapped to their unique identifier, like inode number. Okay. Directories, the file system needs to quickly list the content and find specific file. The inode. I think we will also learn about the inode right in here. The inode, but it is still a long way. Okay. Are often stored in a B3. This allows for rapid lookup of a file by name. When we type ls or dir, there is dir command. Interesting. Dir list directory content. Let me check. So what is it? The difference? We are only listing the file. Is that it? This directory themselves, not their content. Okay. See, there is no lib, right? When we are doing this, there is no lib. This is lib. Okay. Interesting. Yeah, what is the difference then? I think, wait, I kind of forgot. Oh, color, okay. What is it called? Dear Color Auto. Group directories first. Directories first. Yeah, what is the difference between dir and rs? The difference between ls command. Is the code down? Let me check in here. Is there just for backward compatibility? Oh, test C, test B. Yeah, it is an alias on most distro. For this. Yeah, I mean, you can also do this. Like, this is an alias ls on my system. I add color and also group directory first. Something like this. To make it easier to check, is it a directory or a file? That's for backward compatibility. Its output is device independent. Standard for interface generally. Oh, it is not specified by POSIX. Okay. Alright. So it is not the POSIX standard. Okay. Interesting. File metadata in a location in not extend. File aren't just a stream of data, they have metadata. Right, like size, permission, creation date, sending pointers to the actual data block on disk. These metadata structures are often called inodes. Oh, okay. In Unix-like system, for large file, tracking all the scattered data block can be complex. Instead of individual block pointers, many modern file systems use extents. An extent describes a contiguous range of blocks. Start block length of a data block may be described by a list of extents. To manage this extent efficiently, file systems often use bit trees. the key in such a P3 would be logical block address within the file, and the values would be the physical extent on disk. For example, if a file needs to store 1 GB of data instead of 256,004 kilobyte block pointers, it might just need a few dozen extent entries in a P3, significantly reducing the metadata and improving lookup efficiency. I am still not sure what extent in here means. Yeah, maybe we will learn that on the later chapter. Free space management. File system need to keep track of which blocks are free and which are occupied, where simple bitmaps can work for this. For very large volume or to find large contiguous free extents quickly, can be used to index free space. Okay. There is P+3. Okay. While often used interchangeably in general discussion, it's worth noting the primary difference. Internal nodes can store both keys and data pointers. Our data can potentially be found at any level of tree. Our data is stored exclusively in the leaf nodes. Okay. Only contain keys indicates indices to guide the search. Additionally, leaf nodes are typically linked together in a sequential list. Buffer for file system and database. Oh, okay. So we are using P+3 or this P3. Efficient range queries. Since our data is in the leaf and the leaf are linked, traversing data sequentially or performing range queries, find a file created between January 1st and January 31st is very efficient. Okay. Our data in the leaf and the leaf are linked. Traversing data sequentially is very efficient. Okay. You just find the start and follow the linked list of leaf. More key in internal node because internal nodes only store keys, not data pointer. More keys can fit into a single disk block, increasing the fan out and further reducing the tree's height. This minimizes disk input-output for search. Okay. If we rely on P+3, most modern relational database. Limitation and trade-off without complexity and trade-off. Implementation complexity. Building a robust and performant P3 implementation, especially with concurrency and crash recovery in mind, is a non-trivial task. The logic for splitting, merging, and rebalancing nodes can be intricate. Space overhead B-trees by design require a certain fill factor. Nodes are typically kept at least half full. Okay. This means there is some unused space within nodes. It is a trade-off for the performance benefit of contiguous disk blocks. However, this overhead is usually small compared to the overall data size and is vastly outweighed by the I/O efficiency. Small files. For extremely small files, a few bytes, the overhead of managing them within a B-tree structure makes them disproportionate. File systems often have optimization for this, such as storing very small files directly within the directory entry or in node itself, called the inline data or resident data. Okay, to avoid allocating spared data blocks and B-tree entries. Conclusion: the unsung hero of data storage. B-trees are a fundamental cornerstone of modern computing, silently orchestrating how your digital life is stored and retrieved. From the humble text file to a massive database that doesn't directly address the physical reality of disk storage, minimizing slow input-output operation, and providing blazing fast access to vast amount of data. The next time you instantly open a file, take a moment to appreciate the elegant, balanced structure of the B-tree working diligently behind the scenes, ensuring your file system truly stores stuff with remarkable efficiency and reliability. Alright, so that's a little bit about B-tree. Okay. Let's continue here. To make different. Okay, where is it? Some kind of intricate write protocol and write carefully. Okay. To make different common operation efficient, file system employ many different data structure and access method, from simple lists to complex B-trees. If all of this doesn't make sense yet, good. Okay. We'll be talking about all of this quite a bit more in the third part or the third pieces of this book with this persistence, where we'll discuss the files and input-output in general, and then takes rates and file system in great detail. What is rate again? I kind of forgot. Redundant array of inexpensive disks. Okay. Design goal. Okay. I think we will continue this on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.